the Riemann sum of any sampling collection converges, and we called it the integral of the function, and the function is called integrable. Okay, so not all functions are integrable. Okay, so consider, for example, consider f of x as 0 if x is rational, 1 if not. Okay. Let's take this on the interval 0, 1. Okay, so I think I can take it on the interval 0, 1. Okay. Take this function on 0, 1. Okay. Okay, so partition 0, 1 into n equal subintervals. As the first sampling set, choose xk star in xk minus 1 xk as a rational point. Okay. In every interval, we know that there are infinitely many rational points, infinitely many irrational points. So we choose always a rational point. For this sampling set, we form the Riemann sum, summation k equals 1 to n, f of xk star delta x. Okay. But x is rational, so this is 0. This is 0 since all xk star are rational. Okay, and f rational equals 0 by definition. Okay. So let us be pedantic and let's take the limit of this. Okay. So limit as n goes to infinity of k equals 1 to n f xk star delta x is equal to 0 for this sampling set. As the second sampling set, okay, now we choose these irrational. Choose xk star in this interval as irrational. Okay. Then summation, okay, so let me take this. The limit as n goes to infinity, summation k equals from 1 to n, Riemann sum for the sampling set delta x is equal to n goes to infinity, summation k equals 1 to n delta x. Okay, each of these, this is equal to 1 since f irrational is equal to 1. Okay. But if you add these things, you get the length of the interval. Okay, so this is 0, 1, and we have these things. This is delta x, this is delta x, this is delta x, delta x, delta x. So if I add them, I get 1. Okay. So these two limits do not agree. Okay, so this and this. Okay, these limits do not agree. Do not agree. So f is, let me say, this f is not integrable. Actually, we showed that it is not integrable on 0, 1. But you see the way we showed it works for any interval. Okay? By this choice, no matter which interval you choose, this sampling set will give you 0, and this sampling set will give you the length of the interval. Okay, so those two limits do not exist. By definition, we agreed to call a function integrable if no matter which sampling set you choose, the limits will converge to the same number. So this f is not integrable. Okay, then the question is which functions are integrable? Okay, so we are coming there. Okay. So next question is, which function, how do we recognize integrable functions? So I think that's a more reasonable question, because which functions are integrable is a question we don't know how to answer, but we know a big subset of this. How do we detect integrable functions? So first observation is the following. If somehow we know that f is integrable, now how do we know that f is integrable? Somehow we manage to know that no matter which sampling set you choose, these Riemann sums will converge to the same number. Okay, now tautologically, if for every choice of sampling sets it converges to the same number, then you can choose nice, understandable sampling set. It will also converge to the same number, because I already mentioned that all of these things converge to the same limit. So I choose one particular nice thing. Okay, then any nice choice of sampling set will give a Riemann sum which converges to the same integral. Okay, remember that we called that limit the integral of the function, so that it will converge to the same limit. For example, x, k star can be chosen always, can be chosen as always to be xk or xk minus 1 or mean point of f on xk minus 1 xk or max point of f on the interval. Okay, so once somehow if we manage to know that f is integrable, then to find that limit we choose a particular thing. So this is the same concept with limits. If you are taking the limit of a function, okay, if you are taking the limit of a function, and if you know that the limit exists, then you can, instead of taking arbitrary points around that point, you can take a spatial sequence converging to that point, and you evaluate the function there, you get the same limit. Okay? So the big question is, how do I know that a function is integrable without actually doing this impossible calculation? Okay, so this is impossible because you cannot try all possible choices. Okay, but fortunately there is this big theorem. Okay, so let's say big theorem. If f is continuous on a, b, then it is integrable. Okay, so the proof of this thing is not very complicated, but we don't do this in calculus because the ideas used in the proof will never be used again in the problems we solve in calculus. So this generally we do in second year analysis books. It has something to do with so you see, you can always choose the minimum and maximum. Why? Because if f is continuous on every closed and bounded interval, it has a minimum and maximum. You divide this into n equal subintervals. Each subinterval is closed and bounded, so f has a minimum and maximum there. So you have now upper and lower Riemann sums. Any sampling will give you a Riemann sum in between these, because now I managed to get hold of minimum and maximum. So all you have to do is to show that these things converge. Okay, they converge to the same thing. So what happens is that on a small interval here, at this point the function is minimum, at this point the function is maximum. By taking the interval smaller and smaller, can I make these differences as less than by some number? Okay. Well, if I'm only talking about this interval, I can do it because f is small. Suppose I choose an epsilon in my mind, so I can make this interval smaller so that the difference between them will be epsilon. So I can show that eventually the difference between upper and lower Riemann sums will be less than epsilon. But the problem is, on the next interval, when I make this small, you see I'm taking equal subintervals. So when this is small, the other one is small. So I have the minimum here and maximum here. I can make these things small to make the difference between them less than epsilon. But in the nearby interval, will this difference be less than epsilon also? Maybe here I need a smaller thing. But when I make these things small, remember I'm dividing by n. I'm adding new intervals. Okay, so I have to check this in every interval separately. Okay, so there's a big problem here. Fortunately, if f is continuous, you can control all of these at once. That's some concept, if you want to look it up in Wikipedia, that's called uniform convergence. Okay, uniform implies that I can find one small length here so that on every interval of the same length, the difference between minimum and maximum is less than epsilon. Okay, so that's something continuous functions. That's the bottleneck in the proof of this. To prove that a continuous function is uniformly continuous. Okay, so once you have that theorem, the rest is easy because this is the idea. You say on every interval, I'll take these things small so that on every interval, the difference between minimum and maximum is less than epsilon, and then the rest is easy. And upper Riemann sum and lower Riemann sum, you can show will converge to the same thing. Okay, because you see, lower Riemann sum is increasing, but it is bounded from above, so it goes to a limit. The other one also is decreasing, but bounded from below, so it goes to a limit. So the only thing now you have to show is that these limits are the same. But you can show, with this argument, you can show that the difference between these two limits is less than epsilon, no matter which epsilon you choose. So they are the same. Okay, so the second part of the proof is trivial. The big part is to show that for a continuous function, I can uniformly control the difference between minimum and maximum. So that's why we don't give the proof of this thing. But now we suddenly have a big theorem because we recognize that we recognize continuous functions. They are all integrable. And this observation, this trivial observation says that now since I know the function is integrable, I don't need to consider all possible Riemann sums. I only choose easy ones. In fact, I can only choose this one. At every interval, I choose the minimum point, just one Riemann sum. Take the limit. If the limit exists, well, if the limit exists, I take the limit. If I can calculate the limit as a number, that number is the integral. Okay? So that's why this big theorem, sometimes it's called the Riemann theorem. So let's see what we have next on the agenda. So we talk about these things. So another thing to talk about is that, well, I think we can talk about this when time comes. We define, to make life easier, we defined this integral concept using equal subintervals. But you may notice that the subintervals need not be equal. You can choose arbitrary subintervals. But this time what you want is that the maximum length of the subintervals of all intervals must go to 0. So let me just make a note of this to keep in mind. Okay, but you see, if the function is continuous, it's integrable, so it doesn't matter which particular choice you do along the way of taking the limit. The limit exists, so spatially chosen partitions will give you the same limit. Okay, so remark, we chose to use equal subintervals on A, B for the Riemann sum. Okay, but we can also use unequal partitions. Okay, so for example, this is A, this is B. So we take these things. Okay, so this is x1, x2, x3, etc. So each part is, let's go, now we can call them xk, delta xk. Each delta xk is probably different. Okay. So this time the integral will be defined as, first I form the Riemann sum. Okay, so k equals from 1 to n. I evaluate the function at my sampling point. I multiply it with delta xk. So this part is geometric, right? This is the base of the rectangle. This is the height of the rectangle. I calculate the area of this rectangle. I add them up. Okay, now I don't take the limit as n goes to infinity. I take the limit as maximum delta k goes to 0. Okay, so this is equivalent to saying that I'm choosing larger and larger n, because in order to make these things small, I have to add more points. And I don't keep any of the intervals fixed. Okay, the length of the intervals go to 0. Okay, so this is, if this limit exists, then we call it the integral. Okay, but we will not use this very often. Okay, so that was a remark I wanted to make. So okay, so let's do some numerical examples, and then we'll talk about why we do all of this in calculus. Okay, but I think I'll start this later after I do some numerical examples. Okay, now if we know f is continuous on A, B, then we know it is integrable on A, B. So what is the advantage of knowing this. So we can form convenient Riemann sums and take the limit this limit will be, I used f, integral of f w dw from w equals a to w equals b. Okay, so remember I can use any dummy variable there. Okay, so this convenient is convenient to work with in the sum, in the Riemann sum and in the limit. Okay, so in particular, if you are writing the Riemann sum, you want to, well, of course, you don't do this by hand. You just write a 1-line or 2-line program. To the program, you have to tell which sampling points to choose. Okay, so there you want to give a rule. Say always choose the left-hand side, always choose the right-hand side, or choose the middle point. Okay, so if you know that f is continuous, that will work. If you if you are doing this by hand, then this convenient means that you write the Riemann sum and then simplify it and come up with the formula, just like the one we did with x square. Okay, with the x square, you write the Riemann sum, and then we know that the result is a polynomial. Okay, well, actually a polynomial divided by n cubed, and then you take the limit. But if you are doing this with a computer, then you don't need to simplify the sum. The computer will take the sum, next sum, and add it to the previous sum. Well, it will calculate the areas of rectangles one by one and add them. So all you have to do is tell them exactly how to calculate the height of the rectangle. Okay, so that's the choice of the point. That's the sampling point. Okay, so let us do some examples. So for example, okay, so this example, let f of x equals x cubed plus cosine x plus 1 plus 1 plus x on 3,11. Okay, so f is integrable, f is continuous on 3,11. Okay, so x cubed is continuous everywhere, cosine x is continuous everywhere. 1 over 1 plus x is continuous everywhere except when x equals -1, and x equals -1 is not here. So the sum is continuous everywhere except at x equals -1, and in particular it is continuous on our interval. Then f is integrable on 3,11. So we can form Riemann sums. Okay, so we can form special Riemann sums and know that they converge to integral 3,11 f of x dx. Okay, so in this case, we form this one. So let delta x be 11 minus 3 over n. So this is 8 over n. Okay. Then xi, so instead of k, I'm using I now. You start from 3, and you keep adding these intervals. Okay, so this is I times delta x. So this is 3 plus 8i over n. Okay. So Riemann sum, let's say Riemann sum n. This, we are talking about this particular Riemann sum. Now I'm using I. Okay. F of xi. I'm choosing. Okay, so let xi star be xi. Okay, so what the heck? I can choose anything I like because the big theorem tells me that. Okay, so I can choose nice, convenient points and work only one Riemann sum instead of all possible Riemann sums. And then if the limit, and I know the limit exists. So since I know the limit exists, if I take larger and larger n, this will converge. So here I have this. Okay, so I work with this Riemann sum. I know from the continuity that as n increases, this thing will be a nice approximation for the integral. Okay, so we write this thing. Okay, so this is Rn. Okay, now we give this to a computer, because you see, when you are going to give this computer, this part is easy. It is this part you must specify. You cannot ask the computer to try all possible sampling points, obviously. No one can do that. But this theory tells us that here I can give one specific point. So what I found is that R10 is equal to 4079. You see, the number is large because of this thing. Okay, this is always between plus or minus 1. This thing becomes, this is a little bit small, but this one is increasing. Okay, so R100 is equal to 3692, and 1000 is equal to 3645. R10,000 is equal to 3640. R100,000 is 3640. So I convinced myself that for the area under this curve is probably this number. Okay, so in fact, the actual area is this, but it has point something here. All these numbers, obviously, you notice that has point something here, point something here. I'm not writing them down. Okay. So this is a nice way of getting these numbers. But now let us do something a little bit more exciting. Let us use Riemann sums to calculate pi. So we try to find an area which is related to pi, okay, and then we find an area which is pi, and then we form Riemann sum to calculate this, and it will approximate pi. Okay, so the second example. So we ask what is this is 0 to 1, 1 minus x squared dx equals what? Okay, so one way of doing this is, of course, doing the Riemann sum. Another way we will do later, of course. That's why we are doing this in calculus. We have an exact formula to calculate these things. That will come after the fundamental theorem of calculus, which relates these to differentiation. Another thing is to look at the shape, because we recognize this. This is this is y equals this thing is a square, a circle. Okay, so the picture is this. Okay, so we have this. So this is y equals 1 minus x squared, or in other words, we are looking at this. Okay, so the integral gives this shaded area, which is pi over 4, right? Pi r squared, r is 1, the whole area is pi, this is pi over 4. Okay, so we know the value of this integral without doing any calculation. Well, because it's because just playing with words. When you say this integral, if the function is positive, we talk about the area under that. Okay, so in particular, if I look at this funny function, 1 minus x squared dx, this is equal to pi. Okay, so let us take f of x as 4 times square root 1 minus x squared. Let us take delta x as 1 over n. We divide the interval 0, 1 into n equals subintervals. Let us again take the left-hand side or right-hand side. Let us take xi equals in. Okay, we are taking the right-hand side. So we are taking the minimum. We look at the Riemann sum. But this time I wrote n like this. So this is summation I equals from 1 to n f of xi delta xi. Okay, so I don't need to write the expression here because we are not going to do it by hand. So you just you just define the function f to the computer, and you also define this delta x. Okay. So now let us look at the numbers. Okay, R100 is equal to 3.1204. R1000 is equal to 31395. Okay, so this thing 10,000 is 31413. Then I take 100,000. Okay, so with the computer, it all depends on your patient. 15. I take 200,000. I get again the same thing. Of course, when you do this to a computer, it depends on how much precision you are giving. So there will be some numbers here. Okay. So I decided to look at only the first 4 things. And if you are patient and if you have courage, you can give it to 1 million, because sometimes the computer takes ages to calculate these things. But you check how much time it took for this thing. Okay, so you just looked around a little bit, you got the answer. So you say, okay, I'll go and get myself coffee, and then it will calculate this. Okay, so now we are convinced that this number, this first 4 digits will not change. Okay, of course, you have to do a little bit more analysis here to convince yourself that these numbers will stay fixed. Okay, but empirically now, this approximates pi quite nicely. Since the function is decreasing, and we are looking at, since we are taking the left-hand side, excuse me, the right-hand side, we are taking the minimum point. So the lower Riemann sum is increasing. Okay, so it increases to this, and here you check what it is doing. So you convince yourself that this is the nice beginning of pi. Now we have some obvious looking examples, properties of integrals. So let me do those, because these are just like those boring properties of limits. Once you write them down, it is obvious, but then at crucial points, you use them. Okay, so for example, you see squeeze theorem, such a convenient theorem, is proved using one of those boring theorems. It says that if this function is always less than or equal to this function, if they both have a limit, then the limit of this cannot exceed the limit of this. Totally obvious, but you have to say such a thing so that a complicated theorem can use this as a proof. So we have some things like that. So let me mention those things, because we need to do a little bit more than just numerical approximation to integrals. In order to do something more precise, we need to remind ourselves that this integral concept is defined using limits. So whatever properties limits have, some of them must pass to integrals. Okay? So let me say some immediate properties of limits, of integrals. Okay, so first let me start with this thing. So I will not follow the numbers. So far, we interpreted integral as the area under a positive function. Okay, so we always looked at something like this, and the area was this. Okay, but when you write the Riemann sum, the Riemann sum does not care about the sum, about the sign of f. Okay, because you just write it like this: k equals from 1 to n. You evaluate f at some, I'm using k now, at some sampling point, then you multiply it by this. Okay, so we defined the integral as the limit of this thing. So here in this Riemann sum, this summation sum doesn't ask f if it is positive or negative. Whatever that number is, it multiplies it with this number. Okay, this number is positive, but again, Riemann sum doesn't ask. You give two numbers to Riemann sum, it multiplies them and add them to the previous sum. So this thing makes sense when f is not always positive. Okay. So if this is the case, okay, so we have this area, then integral of this function. Okay, you are multiplying a length, a positive length, by a negative height. Okay, so you get the area of this rectangle with -1 sign is -1 times the shaded area. Okay. If, moreover, f is such that the graph of this is something like this. Okay, so we start from here, we go like this. Okay, so this area, let's call this area A, this area B, this area C. A, B, C positive numbers are areas of shown regions. Okay, then, so where is C? C is here. Okay, then integral of A, okay, so this is small a, this is B. Integral AB f of x dx is A minus B plus C. If the area is under the x-axis, then integral will calculate that area with a minus sign. If it is above, it will calculate it positively. And if the curve goes up and down, we get this area. There is no universal name for this, but sometimes we call it the signed area. Okay, you have to invent a name just to remind yourselves that the areas under the x-axis are treated as negative areas by the integral. Okay, so this is one property. So what is the second property is, of course, limits are additive, so I think we'll do it in that order. Okay. So next property is, if C is a constant, then integral from A to B C dx is, well, you expect what this is. The graph of this is a rectangle, so this is C times B minus A. Okay, so this is A, this is B, this is C. Y equals C. Okay, so this area. So it's nice, sometimes it's nice to recognize this. And moreover, we have A, B, f of x plus g of x dx. We are assuming that f and g are integrable. Okay, so if you add two integrable functions, you get an integrable function. Okay, this is summation a b f of x dx plus a b g of x dx, assuming that f and g are integrable. F and g are integrable. In fact, in most cases we'll be doing in calculus, they will be continuous function, and even since most of our functions are differentiable, we will be dealing with differentiable nice functions. We can multiply. You see, this follows because this thing is given as the limit of a Riemann sum, but limit is additive. Okay, so that's where it comes from. And in the limit, if you multiply a function and take the limit, it is that number times the limit of the function. So that translates into integration like this. Okay, let's see what other properties we have. So we looked at this thing. Well, okay, the book gives this as a different rule, so I'll just make it here. Okay, so this minus sign, it's just to make life easier. You see, if I have minus here, I can see this as plus minus g. And then here I have plus, and here I have minus g. But minus is a constant. It comes out. Okay, so that's not a new rule, but easy to remember. Okay, so I think we have one more thing about okay, so this one is again, so these things, for these properties follow from properties of limits. This property now follows from the interpretation of this thing as an area. So if you have a b f of x dx plus integral b to c f of x dx equals. So let us look at what this is saying. I have on the coordinate system here, I have a here, b here, and c here. So suppose the function is something like this. Suppose it's always positive. Okay. So the first integral is giving me the area here, integral from a to b, area here. So this is my function y equals f of x. The second integral is giving the area from b to c. And I'm adding those things. So how do I express it? I express it as the area from a to c. Okay? So this is the integral from a to c f of x dx. Okay? So this looks total trivial again, but as I said, these total trivial things later on make very complicated calculations easy. Okay? And we have, using this, I think we can do one more thing. I can return. So where do I? Okay, so maybe I'll just edit myself. Okay, another property. So you see this integral a to b f of x dx is a Riemann sum. I'm taking the sum of rectangles from this side to the other side. Here the crucial thing is that I'm calculating dx as this point minus this point divided by n. Okay? So we didn't pay attention to this, but this is how we define this. Now if I write this thing, okay, so Riemann integral will not care whether I write this number first or this number. Riemann integral will do again this number minus this number divided by n. So that's what algebra does. Okay? So algebra is not fooled by the color of the pen you are using, whether you are looking right or left. Okay? You give a formula, algebra follows that formula. But now see what happened here. This number is minus 1 times this number. Okay? So let us call this thing tilde. This is equal to minus delta x. And then in each subinterval, you are evaluating this function. Okay, so here you'll do the same thing. But now the sum, the Riemann sum you get here will be minus 1 times the Riemann sum you get here, because this minus comes from delta x. Therefore, this integral here is going to be minus 1 times this integral. Okay? So this is, again, total trivial, but sometimes you need this, sometimes, because this is very useful despite its innocent face. This thing is very useful. Sometimes you have integral from a to b, and you have integral c to b. Okay, so you want to turn it so that these things will match, and you can add them. And that, you see, it simplifies things. Instead of working with two integrals, you collapse it to one integral, and then you work it. That we will do in the proof of the fundamental theorem of calculus. Okay, so again, a total trivial observation, but useful. So another thing we have is about inequalities. Okay, so maybe we do that. Okay, so this is if f of x is less than or equal to g of x on the interval a, b, we are assuming that they are integrable, okay, or continuous to be on the safe side. Then the integral of f of x dx from a to b is less than or equal to integral ab g of x d of x. Okay? So this helps us to approximate integrals sometimes, because even though later on we'll find very powerful techniques to evaluate the integrals, sometimes the function you have here is very complicated. Our techniques will not work, but nonetheless you want an approximation. Sometimes the Riemann sum works, but Riemann sum is a big activity. Okay, you have to write a program, run the numbers, etc. Sometimes you don't need that much precision. You just want upper and lower limits for this. So you find a nice function which you can integrate, and it is larger than this. You find a nice function less than this, which is integrable, and then the integral of this part is less than this, and the integral of this part larger than this. So this number is between these two numbers. So what are easiest numbers for this? So let me do that, and maybe I think we can then stop here. And on Friday, we'll tie all of this to differentiation. Okay, so nice choice here. So following the previous property, observation, let f be continuous on AB. Okay, then f is continuous on a closed and bounded set. F has a minimum, maximum. Then f is integrable on AB, and f has a minimum, say m, and a maximum, say big M, on AB. Okay, so all of these are consequences of noticing that f is a continuous function. Okay? Then we have f of x is always less than or equal to capital maximum and minimum for all x on this interval AB. Okay, now I use the previous observation that then integrals of this, integral of m dx from a to b is less than or equal to integral ab f of x dx. That's less than or equal to integral from a to b m dx. Okay? But now these are totally trivial to evaluate. Okay, so I can evaluate this. This is m times b minus a. That is less than or equal to this interval, f of x dx, and that is m b minus a. Okay, so we can even, we know that this holds. Sometimes it is difficult to precisely find out what m is. Okay, so we can even say m prime times b minus a less than or equal to this interval, f of x dx less than or equal to big M prime b minus a, where m prime is any number less than or equal to m, and m prime is any number larger than or equal to m. Okay, so sometimes you see to find the minima and maxima requires some work, But you see, for example, you can check that f is such that it will never be larger than 5. Okay, so you are not sure whether it will be always less than 4, but you are sure that it will always be less than 5. So you don't need to calculate m here. Now here you can take 5. Okay. In most cases of interest, we find these numbers close to each other. So this thing on a small interval, obviously these numbers are close to each other. So you can have an understanding about the integral. We use this thing again. This looks very totally trivial to you, but then we divide this integral by something and then take the limit as that something goes to 0, etc. In taking limits, you see this. I don't know what this number is, but I know that that number is between these two things. So if I can use take limits of these endpoints and they go to the same thing, then this goes to the same limit if I'm taking limits. That we will do because these things will be parameters on Friday and we'll take limits. Okay, so that's all for today. On Friday, we will do the fundamental theorem of calculus, which relates integration to differentiation, and that will explain why we are doing this in calculus. Yes, of course. You always have our surprise quiz. İntegralle alakalı olacak, evet. Riemann sumlarla. En kolayı Riemann sumlar ya.